And we are live. Today no fun, because after the rain the temperature has been a little more bearable. Now we were looking at this library for Perlin noise. And as of right now, nothing really is happening. Yeah, first thing first, I should add the terrain scale when generating base mesh. Float scale, let's call it 10 for now. Terrain extent, maybe it's better. Okay, so when building the terrain mesh, the X, we got the percentage, and then we multiply it by the terrain extent. Because I used the Z and the X here, so okay, let's say times terrain extent times terrain extent. Things should, yeah, look somewhat better. Like the terrain is obviously bigger. There is some wraparound, yeah, right here, no problem. Can also see that I should add map mapping, but whatever, for now it's cool. When the monk is at 10, yeah, it makes sense. Yeah, okay, it's correct, fantastic. So now it's basically bigger. Okay, so add the terrain extent, commit, push. So okay, now we can generate the terrain, the heights basically. How? Using something like this. Seed type, seed, fantastic. Const seed Perlin noise Perlin seed Perlin octave 2D01. So type, okay. The type devs are Perlin noise Bayesian double. Well, whatever. basic Berlin noise, basic Berlin noise, basic Berlin noise. Reseed, okay, serialization, serialize the serialize, noise, noise 1D, noise 2D, noise 3D. The result, so there is in the range minus 1 1. The result is remapped to the range 0 1. Oh, okay. Octave, the result can be out of range. Octave noise is clamped to the range minus 1 1. So octave 1D, so this is octave 1D, octave 2D, octave 3D, octave 1D 1 1, 1 1, okay. The result is clamped and remapped to the range 0 1. X, octaves, persistence. So with the noise we just get the X and Y. Then here so I should brush up on Berlin noise though. Oops. Frequency, octaves and seed. So Berlin noise. Fantastic. If I look for Berlin noise, Berlin noise, octaves, persistence, frequency, octaves and okay, frequency. Let's look. Oh my god, very readable, I would say. So secondary we found not okay. Many people have used random number generators in their programs to create unpredictability, make the motion and behavior of objects appear more natural, or generate textures. Random number generators certainly have their uses, but at times their output can be too harsh to appear natural. This article will present a function which has a very wide range of uses, more than I can think of, but basically anywhere where you need something to look natural in origin. What's more, its output can easily be tailored to suit your needs. So if you look at many things in nature, you will notice that they are fractal. They have various levels of detail. A common example is the outline of a mountain range. It contains large variations in height, the mountains, medium variations, the hills, small variations, the boulders, tiny variations, the stones, etc. You could go on. Look at almost anything: the distribution of patchy grass on a field, waves in the sea, the movements of an ant, the movement of branches of a tree, patterns in marble, winds. All these phenomena exhibit the same pattern of large and small variations. The Perlin noise function recreates this by simply adding up noising functions at a range of different scales. To create the Perlin noise function, you will need two things: a noise function and an interpolation function. Introduction to noise function. Okay, it goes in detail. Fantastic. A noise function is essentially a seeded random number generator. It takes an integer as a parameter and returns a random number based on that parameter. If you pass it the same parameter twice, it produces the same number twice. It is very important that it behaves in this way, otherwise the Perlin function will simply produce nonsense. Here is a graph showing an example noise function. A random value between 0 and 1 is assigned to every point on the x-axis, whatever. By smoothly interpolating between the values, we can define a contiguous function that takes a non-integer as a parameter. I will discuss various ways of interpolating the values later. Definitions. Before I go any further, let me define what I mean by amplitude and frequency. If you have studied physics, you may well have come across the concept of amplitude and frequency applied to a sine wave. Sine wave, this is the classic sine wave. The wavelength of a sine wave is the distance from one peak to another. The amplitude is the height of the wave. The frequency is defined to be 1 over the wavelength. Fantastic. So the amplitude is the height of the wave. The wavelength is the distance between one peak to the other. Noise wave. In the graph of this example noise function, the red spots indicate the random values defined along the dimension of the function. In this case, the amplitude is the difference between the minimum and maximum values the function could have. So the minimum is this, I think, and the maximum would be this. So this minus this would be the amplitude. The wavelength is the distance from one red spot to the next. Again, the frequency is defined to be 1 over the wavelength, creating the Perlin noise function. Now, if you take lots of such smooth functions with various frequencies and amplitudes, you can add them all together to create a nice noise function. This is the Perlin noise function. So we got this first noise function with amplitude 128 and frequency 4. We have this other noise function with amplitude 64 and frequency 8, so narrower in codomain, higher frequency, so this means smaller wavelength. We have this amplitude 32, so even narrower, and the frequency is 16, so bigger frequency means even smaller wavelength. This amplitude 16, frequency 32, amplitude 8, so we decrease the amplitude and we increase the frequency, So we decrease the amplitude and we decrease the wavelength, basically. Amplitude 8, frequency 64. Amplitude 4, frequency 128. Sum of the noise functions, here is the Perlin noise. Add them together and this is what you get. You can see that this function has large, medium and small variations. You may even imagine that it looks a little like a mountain range. In fact, many computer-generated landscapes are made using this method. Of course, they use 2D noise, which I shall get onto in a moment. You can, of course, do the same in 2 dimensions. Some noise functions are created in 2D, and you get those noise functions. Add all these functions together, produce this noisy pattern. Persistence. When you're adding together these noise functions, you may wonder exactly what amplitude and frequency to use for each one. The one-dimensional example above used twice the frequency and half the amplitude for each successive noise function added. Okay, so the one-dimensional example above, so when you're adding together those noise functions, you may wonder exactly what amplitude and frequency to use for each one. The one-dimensional example above used twice the frequency, yes, 4, 8, 16, 32, and half the amplitude. For successive noise function. This is quite common. So common in fact that many people don't even consider using anything else. However, you can create Perlin noise functions with different characteristics by using other frequencies and amplitudes for each step. For example, to create a smooth rolling hills, you could use Perlin noise function with large amplitudes for the low frequencies and very small amplitudes for the higher frequencies. Or you could make a flat but very rocky plane, choosing low amplitudes for low frequencies. To make it simpler and to avoid repeating the words amplitude and frequency all the time, a single number is used to specify the amplitude of each frequency. This value is known as persistence. There is some ambiguity as to its exact meaning. The term was originally coined by Mandelbrot, one of the people behind the discovery of fractals. He defined noise with a lot of high frequency as having a low persistence. My friend Matt also came up with the concept of persistence, but defined it the other way around. To be honest, I prefer Matt's definition. Sorry, Mandelbrot. So our definition of persistence is this: frequency is 2 to the I, the amplitude is the persistence to the I. Okay, the I is the ith noise function being added. To illustrate the effect of persistence on the output of the Perlin noise, take a look at the diagrams below. They show the component noise functions that are added, the effect of the persistent value, and the resultant Perlin noise function. So we have frequency, amplitude, persistence is 1/4, so the frequency is 2. So each of the frequency gets doubled. The amplitude gets 1/4 divided by 4, basically. Okay. Persistence 1/2. The amplitude gets divided by 2, basically, every time. The persistence is 1 over the square root of 2. Okay. The persistence is 1. Okay. So they show the okay. So the frequency is 2 to the I and amplitude is the persistence. Okay. It's just a successive noise function you add is known as an octave. Oops. Sorry. Got a Sorry, got a message. So octaves. Each successive noise function you add is known as an octave. Okay, the reason for this is that each noise function is twice the frequency of the previous one. So each successive noise function you add is known as an octave. Each noise function is known as an octave. Okay, the reason for this is that each noise function is twice the frequency, okay, of the previous one. In music, octaves also have this property. Okay, exactly how many octaves you add together is entirely up to you. You may add as many or as few as you want. However, let me give you some suggestions. If you're using the perlite noise function to render an image to the screen, there will come a point when an octave has too high a frequency to be displayable. Okay. There simply may not be enough pixels on the screen to reproduce all the little details of a very high frequency noise function. Some implementations of perlite noise automatically add up as many noise functions they can until the limits of the screen or other medium are reached. It is also wise to stop adding noise functions when their amplitude becomes too small to reproduce. Exactly when that happens depends on the level of persistence, the overall amplitude of the perlite function, and the bit resolution of your screen or whatever. Making your noise functions. What do we look for in a noise function? Well, it is essentially a random number generator. However, unlike other random number generators you may have come across in your programs, which give you a different random number every time you call them, these noise functions supply a random number calculated from one or more parameters, i.e. every time you pass the same number to the noise function, it will respond with the same number but pass it a different number and it will return a different number. I don't know a lot about number generators, so I'm looking for some. Okay. Now you want to several different number generators, you're making several copies of them but usually different numbers. Okay, you do your interpolation. Okay. Linear interpolation is horrible. Cosine interpolation. This method gives a much smoother curve than linear interpolation. It's clearly better and worth the effort if you can afford a very slight loss in speed. Cosine interpolate can be x ft x times pi f equals 1 minus cos ft times 0.5. Return a times 1 minus f plus b times f. End of function. Cool. Cubic. Applications of perlite noise. Now that you have a fantastic function, okay. Living objects rarely stay still for very long, except students. Use perlite noise to consistently adjust the joint positions of a virtual human player in a game, for example, to make it look like it's more alive. During sketched lines, computer-drawn lines are always totally straight, which can make them look unnatural and unfriendly. You can use perlite noise to introduce a wobbliness to a line drawing algorithm, to make it appear as if it's been drawn by hand. You can also draw wobbly circles and boxes. Some research has been done on making a sketchy user interface. Informal looking interfaces. Makes sense. Two-dimensional. These are landscapes. These are perfect application for 2D Berlin noise. Unlike the subdivision method, you do not have to store the landscape anywhere in memory. The height of any point of the landscape can be calculated easily. That's what's more, the land stretches infinitely, almost, and can be calculated to minute detail. So it's perfect of variable level of detail rendering. It's perfect for. The properties of the landscape can be defined easily too. Clouds. Again, cloud rendering is well suited to Berlin noise, okay. Generating textures. All sorts of textures can be generated using Berlin noise. The textures generated can go on for ages before repeating, if ever, which makes them much more pleasant to look at than a repeating tile texture map. 3D. So 3-dimensional noise. 3D clouds. You can of course produce volumetric clouds. You'll probably have to use some sort of ray tracing to visualize them. Animated clouds. You can produce animated 2-dimensional clouds with 3D Berlin noise, if you consider one dimension to be time, of course. Clouds. Solid textures. Some rendering ray tracing programs like POV Ray apply texture to objects by literally carving them from a 3-dimensional texture. This way, the textures do not suffer from the wrapping usually associated with mapping 2D textures onto non-flat 3D objects. 4-dimensional animated 3D textures and clouds. Moving into higher dimensions, you can easily produce animated clouds and solid textures. Just consider the extra dimension to be time. Okay. Berlin is fantastic for generating textures. You can produce textures that are, for all practical purposes, infinitely large, but take up almost no memory. You can create marble, wood, swirly patterns, probably anything if you try hard. Okay. You can also define a 3D texture. You can think of this as a solid block of material from which you can carve an object. This allows you to produce textures which can be applied to any shaped object without distortion. It can take a lot of imagination, though, and experimentation to get texture to look really good. Use a pairing function to create different persistencies and different frequencies in different dimensions. You can use one pairing function to affect the properties of another. You can create harder edges to the Berlin noise by applying a function to the output. To create more interesting and complicated textures, you should try making some Berlin functions. This texture was created in two parts. Firstly, a Berlin function with low persistence was used to define the shape of the blobs. The value, because the persistence is defined as persistence. Okay. So the persistence is the ith square of the amplitude. Okay. So it's basically the amplitude. It depends on the amplitude. Or sorry, the amplitude in our case is the persistence to the ith. To the ith. They get smaller and smaller, basically. Yeah. So, this family was used to sell from two other. Okay. the value of this function was used to deselect from two other functions, one of which defined the stripes, the other defined the blotchy pattern. A high value choose more of the former, a low value more of the latter. The stripes were defined by multiplying the first Perlin function by some number, about 20, then taking the cosine. Marble texture can be made by using Perlin function as an offset to a cosine function. Lines with textures can be defined. The grain is defined by a low persistent function like this. The very fine bumps you can see on the wood are high frequency noise that has been stretched in one dimension. Cool. Very, very cool. So, now we at least know what is an octave, what is the persistence and whatever. So it did octave to D, the value, the X, the Y, with 4 octaves. Okay. Yeah, let's integrate this. Perlin noise HPP. Let's download it. Now, how do we integrate this in the engine? Well, it's not really that big of a deal. I mean, we go here, we go here, render, we go here. Well, why not downloading the entire thing then? Include Perlin noise, and here we finally here it is. Now we see vendor, Perlin noise, include Perlin noise, including project. Here in the properties, general, additional include directories, project dir, vendor, Perlin noise, include, and up here that's it. Compile. Okay, fantastic. I think, yeah. So XY Okay, so let's just max height, let's say 5 for now. Let's bump up the subdivisions, like let's say 14. To do hard coded. And then for int I terrain dot get index, get point, set point, row call. Okay, fantastic. So the row and the column. Yeah, I don't think it really matters at this point. For int I less than terrain dot get points per side I plus plus, sorry, row for int call less than get points per count, get points count per side, call plus plus terrain set point, row call and the height. The height is exactly as you would expect. So you do something like this. So this is the row call. So this is the Perlin. This is the noise, and this is the noise times terrain max height. Let's see what happens. Static cast float. No problemo. Interesting. What? Looking I mean, we should try to use some other texture, but we're getting a pretty good terrain in my opinion. Like, if I were to like visualize the mesh in RenderDoc, go to the mesh viewer, use a fly cam. Like, yeah, it looks terrainy to me. Oh, okay. Yeah. Looks like a terrain to me, honestly. Fantastic. So we got that. I should probably use like implement a wireframe, like implement wireframe rendering. Rendering the wireframe of meshes. Yeah, I mean, we could do it. Okay, fantastic. So we actually integrated our Berlin noise library, and we got out of it we got the like the height for the terrain. Fantastic, fantastic. Okay, so I think I'll stop here. It's quite late. Started late. Did not get like 1 hour, but integrate Berlin noise library and use it to generate the terrain, to generate a simple terrain. So here it's not to do, but it's not. Commit, push, and and I think we're done for today. Goodbye, have a good night, and see you the next time.